Bismillahirrahmanirrahim. Assalamualaikum. Yes, hello everyone, and today we will be continuing explaining chapter 6 from the textbook Chemical Process Safety by Daniel Kroll and Joseph Lover, and as you know that this book is really great, and you're going to learn a lot by trying to solve problems by yourselves. There are many practical problems. It just makes safety understandable, and how do you undergo those different kind of calculations. So what we are going to be taking today, our chapter today is about fires and explosions. So what does fire do with explosions? Sometimes because of fire we have an explosion, and sometimes because of an explosion you have fire. Okay, so both of them could cause could go with could be a reason because of one of the other. Yeah, so an explosion could be a chemical explosion, it could be a mechanical explosion. So explosion could be because of pressure going through a certain limit and it exceeds that limit, or we could talk also about exceeding a certain pressure. So it could be because of temperature or because of pressure. Talking about fire, what makes things go on fire? And you already know the triangle, in which if you have the fuel and of course the oxygen, and you have the spark, you're going to have fire on. And why does fire go to an explosion? If you have a lot of energy at a certain place that exceed a certain limit, you're going to have an explosion. So all of those things that we're going to explain, and we're going to of course take it in the sense, or in the practical sense, I would say, of process safety or chemical process safety. So just to get an idea before getting to things, so things that we need to remember, and actually these are from chapter number 5, where it is mentioning things about inherent safety. And talking about inherent safety, that means we can build things within the design process to make sure that we have less, for example, inventory or less chemicals. So if you have, for example, within a storage tank, and you're storing within this tank, you're storing a certain amount of a liquid that you want to sell later, whatever is that liquid, and now if that liquid, say benzene for example, and what about the vapor here of benzene? Will it exceed the limit? Of course, we were always talking about exceeding the limit of what? Exceeding the limit, threshold limit value that could be harmful to a person. So he's exposed to that limit. But what about if you are not talking about harmful to a person, but you are talking really about a flammability limit? So flammability limit is different. It is really different from TLV. So here we're talking about a low flammability limit and a high flammability limit, and all that we're going to be taking that soon. So talking about here, we are trying to reduce the inventory, which could be one of the reasons of that triangle, right? One of the reasons. If you have like fuel, we have oxygen, and of course we have the ignition source, right? Igniting source. Talking about the fuel, if we have less fuel, we could have less fire, or we can also prevent the explosion. And most of the time there was more concentration about reducing oxygen, but you can do this, right? You can put off fire by taking off oxygen. But talking about safety now, it's more important to concentrate about reducing the fuel, so that you can take care of that of that triangle here, to have less fuel, a part of less inventory, and of course inherent safety. Talking about both for the threshold limit value and for the flammability limits. And of course you will have some other stuff that you also need to have within your design process, to have better safety, better engineering design, better management for every process, for audits, for equipment testing, for maintenance programs. You need to have specified and written policies and procedures, and people need to be trained how to do that. And of course, talking about sensors, and you need sensors everywhere. And if there's any problem that happens to a person, he needs to spray water, for example, on his face, or water curtain on certain locations to put off fire, and so on. So we also need to consider countermeasures, and just countermeasures as just the quick actions that you have. However, you need also to have emergency responses where you need maybe to take some kind of evacuation, which means run away, run. Okay. So these are the ideas about just to get you into place. We will be talking about fires and explosions, but as we are going to be talking about fires and explosions, we need to consider the inherent idea that how to build things and design it so that we can have some kind of safety. So as we said that chemicals are the main things that which could cause a hazard in an explosion, and a combustion. Just to get an idea, a combustion of 1 gallon of toluene can destroy an ordinary chemistry laboratory in minutes. Persons present in that place may be killed, and the potential consequences of fires and explosions in pilot plants and plants are even greater. So what I'm talking about just 1 gallon of toluene. Okay, this is how dangerous things can be. And the three main common chemical plant accidents that you would see or you would go through, hopefully you don't go through any, but they are fires, explosions, and toxic releases. We talked about toxic release, about the TLV, the threshold limit values. Today we're going to be talking about fires and explosions. Okay, so these are the two things we're going to be talking about. And of course, to prevent accidents that could come from fires and explosions, we need to know how does fire occur, and what makes fire go to an explosion, and how do explosions occur. So we need to know how to deal with those consequences by knowing the fire and explosion properties. Okay, so we need to know the properties of the materials, of the chemicals that we are going to be dealing with. So in this chapter again, we're going to cover 2 or maybe 3 topics. We'll see how it goes, emphasizing of course all the definitions regarding fires and explosions, and of course we are going to later take some procedures how to reduce fire and explosions, and that will be in chapter 7. Okay, so how to reduce fires and explosions is in chapter 7, but how to do the calculations of fires and explosions and how many people could die or get hurt because of that explosion, all will be in chapter 6. This is our chapter. So the first thing that we need to talk about is the fire triangle. The fire triangle has 3 essential elements for combustion. احتراق. Okay, they are fuel, oxidizer, and the ignition source. So the fuel is here, right? The fuel could be CH4, methane, propane, whatever, butane, benzene. Okay, so all hydrocarbons that we have, they are considered as what? As fuel. Okay, so of course wood is fuel and all other those stuff. So hydrocarbons, they are the fuel. Oxygen is oxygen in the air, right? So we know that. What about the third part? It is the heat. So if you go for barbecue, right? You go to barbecue and you put your tikka here, right? Very happy, very with that nice tikka here. Oh my god, what is this line here? Okay, putting and kebab as well. So before you put these things, of course, you have your coal. How did you burn your coal? By using fuel, and your fuel or something like, of course you will not use benzene, that would be really very dangerous to use, but some people do use that, and they suffer. Sometimes they really got injured or fire burned because of that, because of the vapors that come out from benzene. Okay, so let's continue on. So what do you need? You need fire, right? So oxygen is in the air, and you have coal here, right? You have the coal, which has the hydrocarbon thing in it. So all what you need is what? You need this thing here, the matches. So you put the matches, and sometimes this doesn't become really hot. So what do you need to do? You need to have some flow of air, and this is why you use some kind of a fan here. Or how's the fan? I don't know how to draw the fan, but it blows so that you can have more of that heat, because you're putting on more oxygen. Okay, so this is the thing that we could talk about here. So you need heat, fuel, and oxygen. So this is the fire triangle. This is the fire triangle. Oxygen source, of course, it comes from air. Heat sources could come from the sun, it could come from hot surfaces, it could come from sparks. Okay, you see, it could just come from a spark. And actually, you always, when you think of a spark, it always gets into your mind that it should be the current that goes through the wires. But actually, it could be static. Okay, it could be static. And what I mean by static, just to get an idea, if you have clouds, clouds, and you have rain, and what do you have as well? Other than all that, sorry for that. Okay, what did I do? Okay. Okay, so other than all that, what do you have? You have lightning. You have a lightning. And what does lightning come from? They come from static electricity. What does static electricity come from? Okay, so it comes from the vapors, water vapor here. Water vapor, where it goes through certain opening. It doesn't go through certain openings, but through some kind of resistance, you could cause some kind of static electricity, and then you have this lightning. So imagine that you have some static electricity just because of vapors going through an opening, a very small opening. So the sparks could be really dangerous, and it could be a source of heat that could cause the fire. So friction as well. I was searching the word friction here. So friction, chemical actions could cause fire. It could be exothermic reaction or friction. Electrical energy, where we said compression of gases. Why does compression of gases cause heat? Actually, compression of gases, if you compress it, you will increase the temperature, and increase of temperature could go beyond the ignition temperature, and that is part where this gets ignited. Okay, so we got an idea about heat sources and oxygen source. What about the fuel? The fuel could be many different kinds. It could be gas or liquid or a solid. Talking about gases, could be natural gas, propane, butane, hydrocarbons again, right? Liquids, most of them are hydrocarbons, as you can see. Of course, you have kerosene, gasoline, turpentine, and all those you already well know. Olive oil, by the way, is also one kind of the liquids that is flammable, very flammable. And so, of course, solids, you could have coal, wood. Coal is faham, wood, paper, cloth, and many else. So all these are fuel. Okay, so again, what is fire? Fire is, you need these three elements to get fire. Okay, so that is straightforward. So fire is the rapid exothermic oxidation of an ignited fuel. Okay, so when you say the word oxidation here, so it could also mean, it means two things, right? It could mean that it reacts with oxygen, mainly it is that, but it also could mean that there is some kind of loss of electrons. Okay, loss of electrons, and that is why you have some kind of oxidizing agents other than O2. Okay. Which also could cause some kind of exothermic oxidation. That means it gives us very high amount of heat, right? just because of that oxidation process. So oxidation doesn't mean always that it is O2, but most of the cases, yes. The fuel can be in solid, liquid, or vapor. Of course, we already said that. The combustion always occurs in the vapor phase. Okay, so that is one of the key things that you should know. The combustion always occurs in the vapor phase. So it could be that the liquid is flammable, but what happens, the liquid is volatilized, يتبخر, and this is where you can have this kind of combustion. And solids are decomposed into vapor as well before combustion. Okay, so this is what happens. This is where a combustion really occurs. So what do we have? One fuel, oxidizer, and an ignition source. So these are the three elements are present at the necessary levels. Burning will occur. Why did we say at necessary levels? This means that a fire will not occur if fuel is not present, or it is not present in sufficient quantities. Okay, again, fuel is not present, or it is not present in sufficient quantities. So even if you have fuel, oxidizer, and an ignition source, it will not give us fire if it is not present, or sometimes it is present but it is not sufficient. And this also goes with the other element, the second element, which is oxidizer. If you remove oxygen, okay, if you remove oxygen, you will stop fire. But maybe oxygen is not sufficient. It's not enough. And because it is not enough, this is why you have the fire going off. And that's just a small example where you have this kind of a candle. And we have this candle here. When you put a cup or whatever over that candle, it will go on the flame, and slowly it will just go off. Why did it go off? Because there is no oxygen. And actually, there's no sufficient oxygen. It's not that there's no oxygen, there's no sufficient oxygen inside this place here. And mainly it will be some kind of a vacuum in this place, because you already have consumed most of the oxygen in that place here. And this is one of the things that they used to do for what we call hijama. So that is number two. The third element is the ignition source, which is not energetic enough to initiate the fire. So we have some kind of a little spark, but it is not enough to have a fire. So again, we need these three things here: heat, air, and fire. Okay, heat, air, or oxygen, and fuel. So the heat, air, and fuel, so that you can have fire. And an example, wood, air, and match would do it, and this is what we do for barbecue. Or a gasoline, air, and a spark. And of course, when you put on gasoline in your car, of course, the last thing that you want to have there is a spark. Okay, and so if you have a spark, even from the friction of your shoes, that could be very dangerous, okay, because there are a lot of vapors of that gasoline around. So we need to be careful. So these are examples of different fuels, different oxidizers, different ignition sources. So we already gave an example, but these are just written for you. It just gives you an idea. So why are we taking this? We are taking a chapter in fires and explosions. We are going to study how fire happens and how explosion happens. Now we are studying how fire happens. And we are studying the different fuels that could come into your mind, just to get an imagination, get a view of what could be a fuel. So all these liquids in which you already know, gasoline and acetone at least, or ether also, you have maybe taken that in lab, you have seen those. These are really flammable liquids. And solids, of course, you know how if you burn a plastic, that is very harmful to the environment, but we are talking here about that this is flammable, okay? And gases, of course, if you have propane, carbon monoxide, here the combustion happens directly, but here this needs to go to a gas phase so that it combusts. Okay, what are the oxidizers? Oxygen, fluorine, and chlorine. So as I had said, that oxidizers most of the examples that could come to your head is the oxygen. But by the way, fluorine is an oxidizer and chlorine is an oxidizer. And fluorine and chlorine are very, very, very strong oxidizers. And it's just like impossible, because they're an oxidizer, and if you put it in contact, chlorine, if you put that in contact with water, it will just break the water into hydrogen and oxygen. It is to that level that it can take out of that electron, where you have loss of electrons. And because it's a very strong oxidizer, even if you cannot, or it is above that, you cannot put it into a liquid phase, except for a very rare compound. I think it is CCl4 or something like that, but that is a really very dangerous compound. You can read about it. Okay, so that is like tetrafluoride or tetrachloride. I can't remember. I think, yeah, it has chlorine and fluoride, both of them together. You can read about it. Liquids, there are hydrogen peroxide. Hydrogen peroxide is like the Chlorix by youth. Okay, so this is very flammable. You already know about it. And of course, you have solids, which is ammonium nitrite is one of them, which is used also in TNT. All these things that you already know, that these are oxidizers. Ignition sources, sparks, flames, static electricity, heat, all these of course are very clear and obvious that they gives us fire. Spark is like a small fire. Flames is a fire. Static electricity, it gives us the ignition to have a fire. And a heat, of course, could heat up things above a certain limit, where then it auto ignites and becomes fire, right? Okay, great. So in the past, controlling fires and explosion was mainly about what? I already said that. How do we control fires and explosions? We can control fires and explosion by eliminating the ignition sources. So mainly we are saying that we don't want any spark. No sparks, please. No flames. But by the way, yeah, that was the old way of controlling things, which doesn't mean that it is not applicable. It is, but practical experience showed that it is not robust enough. It's not enough. Okay, so this is good, but it's not enough. Why? Because there are other ways of how to catch fire, and because there are other ways of how to catch fires to prevent fires and explosion, it is better also not only to eliminate the ignition sources, but also to focus on preventing flammable mixtures. So we want to concentrate on what? On the material, on the gas, on the mixture of those gases. And which means that we need to study the flammability limits. And by knowing the flammability limits of all the compounds that we have in our system, then we can make sure that this mixture never happens. And if this mixture never happens, that means I will not have fire. Okay, so this is the other way of having an inherent safety, right? Inherent safety. So that is part of the first part, where we covered the triangle, the fire triangle. What is the second part of this chapter? It is how to have a clear distinction between fires and explosions. So fires are not explosions. So what is the difference? Explosions is like a big amount of fire that happens in that very small place, and it happens really very quickly that it will blow everything, right? And that is just the difference. So explosion is like a fire, but it has some kind of additional properties that makes it an explosion. And this is why explosions have a rate of energy, a very high rate of energy. And the release of that rate of energy, it is not slowly as the fire, okay? But it is very rapid. The energy release is very rapid for explosions. It is in the order of microseconds. And that is the big difference between fires can only result from explosions, and explosion can result from fires, of course. But any fires can come from explosions, and explosions can come from fires. But the big difference is that explosions happen like a big amount release of energy that happens in microseconds. And if it is in a very small place, a confined place, that could be really dangerous. Okay, it will blow off everything. And a good example of how the energy release affects the consequences of an accident is a standard automobile tire. And that is a very beautiful example. Very beautiful example how to make just the difference between the idea of fire and explosion. So the compressed air within the tire contains energy. Okay, we know that. Okay, so if the energy is released slowly through the nozzle, the tire is harmfully deflated. So if you try to open, or if you have a nail, okay, if a nail goes in, right, and with that nail that goes in, you're going to have a deflation. So air is going to go up, okay, going out. If the tire ruptures suddenly, okay, suddenly, in like seconds, I mean microseconds, and all of that energy, because of that rupture here, all of that energy just wants to go out from here. What happens? Okay, it blows. Why? Because of the tire ruptures suddenly, and all the energy within that compressed tire releases rapidly, very quickly. And that small space, the result is a dangerous explosion. So did you see the difference? So it's exactly the same, except that that was a rupture, and that is just a small hole in which there's a little release of energy. And of course, that is what happened. I don't know if you went through this. I did not go through what? I went through this. But alhamdulillah, my car was never like that. Yani. So that is like a very dangerous situation that you could go through. Okay, I have a story of something happened like that, but there's no time for that within this video. 6.3. Now we have taken the fire triangle. We know the difference between fires and explosions. Now we want to know what? We need to know some kind of definitions. We need to understand some kind of definitions that will make us more comfortable about when we talk about explosions and fires. So what are the definitions? There are many definitions. The first definition is the combustion of fire. Combustion of fire is a chemical reaction in which a substance combines with the oxidant and releases energy. And again, the word oxidant, that means it takes an electron, but it's an oxygen. Just take it as that. That's fine. Because mainly it is that. Part of the energy release is used to sustain the reaction, of course. So the energy is used to have the reaction going on, but a lot of this energy just goes out. And this is where you have fire. So combustion is what? It is a chemical reaction with oxygen, mainly with oxygen. So it's a chemical reaction with oxygen. What is an ignition then? Is it a difference? It is different from the combustion. Yes, here we are talking about the chemical reaction. Here we are talking about something different. We are talking about an ignition source, masdar lil ihtiraq. Okay, the ignition source of a flammable mixture. So we are mainly talking about the ignition here. So what is ignition? It's the ignition of a flammable mixture, maybe caused by a flammable mixture coming in contact with the source of ignition with sufficient energy. Source of ignition, spark, and a flammable mixture with sufficient energy, or the gas reaching a temperature higher enough to cause the gas to auto-ignite. Okay, so either of them, but it means where it starts to ignite. Okay, it starts to catch fire, right? It starts to catch fire. So that is the ignition. And the example that I can give here, I don't know if you have done this before. So if you take a magnifying glass and you have the sun up here, and you try to concentrate that heat on that small piece of paper, and slowly you will have this changing color, and then it starts blowing and then it is catching up fire. Okay, so why did it catch up fire, right? The only thing that we had, it was heat. I did not put a spark here, but I put a heat. But it went to reaching a temperature high enough to cause the gas to auto-ignite. and in this case it went high enough for that paper to catch up fire. So if it catches up fire like that, so what do we call this? A fixed temperature above which adequate energy is available in the environment to provide an ignition source. So that is an auto ignition temperature. So it will ignite by itself. Ignition could be because of a source. Where's the source? The source here. Here, auto ignition temperature, we are talking about mainly the energy, enough energy for it to catch up and to catch up fire, even if that like source of a spark is not there. Flashpoint, then what is the flashpoint? Flashpoint, is it different or not? Yes, it is different because we're mainly talking about liquids here. The flashpoint of a liquid is the lowest temperature at which it gives off enough vapor to form an ignitable mixture with air. So if you try to heat up things, as I gave the example of this I can go back. As I gave the example of this paper, actually we are having vapors above here, and now these vapors also, they can get more energy until it gets enough energy where it auto ignites. So here we are talking about the flashpoint. However, it will not ignite by itself. We are talking about that we are providing heat, but we are trying to provide heat, and we are a bit by bit till we get this ignitable mixture with air. So we are increasing the temperature slowly till we get to that temperature, which is the lowest temperature for this ignitable mixture with air to ignite. So at the flash point, what happens? The vapor will burn, but only briefly. Inadequate vapor is provided to maintain combustion. Okay, so what happens at this flash point? We have little vapor to catch fire, and we have this combustion, but it will not continue. It will not continue. Fire will not continue. Why does the fire not continue? Because we have inadequate vapor is produced to maintain that combustion only. So there is little energy to maintain that reaction of combustion, but it does not propagate. Okay, so it does not propagate. Okay, it does not propagate. And of course there are many different methods. There are two different methods very popular. It's called the open cup or the closed cup. Okay, open cup, that means open to atmosphere, or closed cup, which is not open to atmosphere, and each one of them just gives us different flash point. And usually the open cup is usually higher. Why? Because it is open to the atmosphere, so some of the vapors do escape and become diluted when it is open to the air. For the closed cup, you have everything really confined, so you will catch up fire quickly. So for example, if I talk about the diesel fuel content and the flash point in motor oils. So what is the flash point for this diesel to catch fire? And in other words, what is the temperature for this diesel to flash, to catch fire in motors? And of course, you can see here two lines, and one of them using the open cup. So the open cup here, the open cup usually it is higher, and the closed cup is here. And here the closed cup, it gives us good idea. Why? Because we have everything in motor oil is closed, and because it is closed, so this will be like giving us a good indication of the flash point. Okay, so what is the flash point? What does it tell me here? It tells me that if you have 1% diesel, this is the temperature in which it's going to ignite, okay, to flash, to give us fire. If you have 2% of diesel, of course you need less temperature. If you have 4% of diesel by volume, this is all by volume. If you have 4% diesel volume of the combustible mixture that we have, 4%, we have about 152 or something like that. So the temperature will be even less and less. So you need less temperature, less heat, okay, for higher diesel content. And I think so this makes just a perfect sense for us. Then what is a fire point? So we already have the flash point, right? We already have the idea of what is a flash point. But actually, the only difference of a flash point and a fire point is the fire point is the lowest temperature at which a vapor above a liquid will continue to burn once ignited. It sounds the same. The fire point temperature is higher than the flash point. The only with the fire point that it starts catching fire. It's not like just a spark and then and it will not propagate, okay? Then it will not propagate. Here we are talking about it catches not only a flash or a spark, but it catches fire, okay? It catches fire and propagates, and then it will propagate. Okay, so that is the difference between the flash point and the fire point, which means that definitely the fire point here, the fire point is higher, so the temperature should be little higher so that it catches up fire. So if this was at 1% the flash point, then maybe the fire point you will have fire would be at a little higher, okay? Then what are the flammability limits? Again, what I'm taking here, I'm taking the definitions. So we have taken the first part, the fire triangle, and then we have taken the second part where we know the difference between the fires and explosions. And now we are taking the third part of knowing the definitions. And knowing the definitions, we have taken many definitions. If you just go catch up, we know what is combustion, which is the chemical reaction, and which releases energy, and part of the energy to keep that combustion, the reaction happening. The second definition is the ignition, where you need a source, but it could auto ignite if you don't have that source, but it goes above a certain amount of energy limit where it ignites by itself. And number three is the definition, which is the flash point, where the difference between flash point is we increase the temperature slowly and till it flashes, till you have the spark temperature, but it does not propagate. But when it propagates, you will have a fire, and where you catch up fire and it just propagates, that is the fire point. Okay, so what's the definition now? The definition we are talking about here is the flammability limit. Flammability limit. So what is the flammability limit? So flammability limit is the limit where you're going to have flames, okay, where you're going to have fire. And you have a lower flammability limit. That means if you reach that limit, you are going to catch fire. And actually, which is surprising maybe for some of you, if you exceed a certain limit, you will also not have fire, right? So it's like there's like a low flammability limit and an upper flammability limit, and between these two limits you will have a flame, you have fire. But lower than that, okay, lower, you will have no flames. Higher, which is also surprising maybe for you, you will have no flames. You will have only flame if you sit within that region. Okay, sorry again, I'm just trying to learn something here, but I'm not getting that clearly. Okay, great. So what do we have here? If we have it lower, you will have no flames or no fire. If you have it higher, you will also have no flames or fire. So it is important to know this, okay? So it will only happen if you have the flame between certain limits, and we call those limits lower flammability limit and the upper flammability limit. And here there are some kind of words that you need to know, so I'm going to read that. The mixture will not burn when the composition is lower than the lower flammability limit. And here the composition is usually in volume percentage. So the volume percentage of benzene is lower than the lower flammability limit. The mixture is too lean, okay? The word lean here, qalil, okay? It's just little for any kind of combustion. And if you go through the mixture, the other part, the mixture is also not combustible. It will not react, okay? It will not react. It's not combustible. It will not react with oxygen when the composition is too rich. Okay, so the opposite of too lean is too rich. So lean and rich. Lean is little, rich is a lot. And so if it is rich with benzene, you have 96% per volume of benzene within air. I mean, imagine, that's too much, huh? That is when it is above the upper flammability limit, it will also not catch fire. It will not react with oxygen. A mixture is flammable only when the composition is between the LFL and the UFL. Commonly used units are volume percent, okay? Volume percent fuel, which is the percentage of fuel plus air, okay? The percentage of fuel plus air. We are going to take many examples, by the way, of how to calculate or how to use the LFL and UFL in the calculations, and to know if we are going to catch up fire or not. So lower explosion limit, oh my god, what is lower explosion limit? You are talking about LFL and UFL. These are other terminologies. They mean the same. They mean the same. But it's important for you to know, because you may hear someone saying lower explosion limit. And actually the lower explosion limit and the upper explosion limits are used interchangeably with the lower flammability limit and the upper flammability limit. Continuing with our definitions. So the next definition we have is the explosion. Okay, so what is the explosion? It is a rapid expansion of gases resulting in a rapidly moving pressure or shock wave. So mainly the explosion, we are talking about the pressure. The pressure goes really high. So you're here talking like the dP by dt. Okay, we have a pressure, and actually it's not only pressure. We also have expansion of gases. So we also have volume. So there is a relationship between dP by dt and volume to give us an idea about the explosion. So the expansion can be mechanical by means of a sudden rupture of a pressurized vessel, and that rupture could be of a pressurized tire. Okay, so just give you an idea, right? Or a pressurized vessel. Or it can be the result of a rapid chemical reaction. Okay, explosion damage is caused by the pressure or shock wave. So that's the explosion. What is the difference between the normal explosion that happens because of a rupture or a chemical reaction? This is the explosion that results from the sudden failure of a vessel, high pressure. So you have a high pressure of a gas within that certain vessel, and the pressure was just too high, pressing here till it blew it out. Okay, so that could be a mechanical explosion. What other definitions do we have? We have something called the deflagration. Deflagration is an explosion. Detonation is an explosion. Confined explosion. Unconfined is an explosion. So all of these, we are talking here about explosions. So the first thing of explosions we have is a mechanical explosion. We have other types of explosion. It could be deflagration. And what is deflagration? It is just an explosion in which that if you have an explosion, the effect of that energy, is like if you have an explosion here, okay, blue, and you're standing here, this will throw you back. Okay, will throw you back. Why it will throw you back? Because you have the push of that explosion moves at a speed. However, the speed is less than the speed of sound. Okay, and if the speed of the explosion happens and the speed is greater than the speed of sound, that means if you're here, but this time it will throw you even further. Okay, it will even throw you further. Okay, it looks like your body expanded because of that. Oh, sorry. So it will throw you really further. So what I'm trying to say, the only difference is that one is less than speed of sound, the other is greater than the speed of sound. What is a confined and unconfined explosion? Confined is a closed vessel, and confined is open. That's the only difference, okay? So an explosion occurring within a vessel or a building, that is called confined. For example, what happens inside the car to explode that amount of fuel that you have in to give you energy is confined. Unconfined explosions, it gets in an open area. And when you talk open area, that means you could have a flammable gas spill, for example, and because of that flammable gas spill, you're going to have this kind of an explosion. Which one is rare? Is confined or the unconfined? Of course, the unconfined are rarer than confined explosions, okay? Because it needs kind of a spill and it stays there where and it waits like for an ignition source for this thing to happen. While as confined explosions, which are inside vessels, are the main which are the frequent one. They are the frequent explosions that have happened throughout our experience. Okay, so what is belief? Belief, it happens where it occurs in a vessel that contains, it's kind of an explosion again, huh? We are talking about explosions still. So belief occurs if a vessel contains a liquid at a temperature above its atmospheric pressure boiling point ruptures. What do you mean? That's a lot in my head. Okay, so what does belief happens? So what happens, you have a container here, okay, that is a vessel, and it happens that there's heat for some reason. For example, there's a cooling system here. Let me say there's a cooling system here, and the cooling system is not working. Because the cooling system is not working, so the temperature inside this vessel is going up. And let's say that this vessel had a volatile compound. Volatile compound, that means it goes and becomes vapor. A volatile قابل للتبخير. Okay, so it's highly volatile compound, so it has a lot of vapors here. Vapors. And imagine how much vapors come here, and it's increasing the pressure inside that tank. Why? Because of the heating process. Okay, there's like, it's not because of the heating process, there's a heat of temperature, or there's a reaction here, whatever it could be. So the cooling system is not working, so the heat is increasing here, and the more heat we have is more vapor of that volatile compound. Now imagine that this blows. If it blows, it really goes very, very high, and it causes a lot of damages. Why? Because it's not only the liquid which is explosive, it's also the vapor cloud that we have is explosive. So let's go back. So belief is the explosive vaporization of a large fraction of the vessel. So so it's like it breaks out from let me show you. It's like it breaks out from here till here, a big fracture, boom, okay, boom, like that. So what happens is that a big fraction of the vessel content, possibly followed by combustion. So after this rupture, you have a combustion or explosion of the cloud, vaporized cloud. Of course, if it is combustible, and we are talking about that it is combustible in this case. This type of explosion occurs when external fire heats the content of the tank, which is volatile. As the tank content heats, the vapor pressure of the liquid within the tank increases, which means they have more vapor. And the tank's structural integrity is reduced, which means the tank cannot withhold this heat because of the high heat, or that high energy, or that high pressure. If the tank ruptures, oh my god, the hot liquid volatilizes very quickly and it explodes. So that is kind of a belief. Another kind of explosions, if you have the dust explosion, so you have a lot of vapors here, oh my god, this is in black and it just makes you crazy, right? So if you have a lot of dust, and within that dust, let me take the red color, okay, So you have a lot of dust and explosions, and because you have a lot of dust and lots of dust here. Dust means what? A very small amount of material. And if you think of it, sometimes things that are very small, they have high surface area, and because they have high surface area, it will be good enough for a fire, right? Good enough for a fire. So what happens here? Many solid materials, including common metals such as iron, aluminum, become flammable when they become like a fine powder. So here we are talking about a very small metals such as iron and aluminum could also be flammable. Okay, could also be flammable. So you're not talking about hydrocarbons. We could have a dust of iron and aluminum powder that could cause an explosion. Shock wave. So if you have an explosion, you have a shock wave. Okay, صدمة wave. It pushes you up as a big wave. So an immediate pressure wave moving through a gas. A shock wave in open air is followed by a strong wind. So the big wind is pushing you away. The combined shock wave and wind is called a blast wave. Okay, so there's a shock wave, and because there's air, this is like a wind, and so both of them they cause a blast wave. Boom, it just throws you really far away. The pressure increase in the shock wave is so rapid that the process is mostly adiabatic, and this is good for some calculations. Okay, the pressure on an object as a result of an impact shock wave. So because of the shock wave, boom, a big pressure, that pressure is called the overpressure. Okay, the overpressure, the pressure on an object as a result of impacting shock wave. So what is the pressure if something blows off here and it comes to me? Okay, so depending on this overpressure, I can tell through experience that if I'm going to die or not. Okay, so I will talk about something simpler. Okay, I don't want to die here. Okay, so if I have a big building, okay, that's big building. If I know what is the overpressure that hits that building because of that explosion, I can also identify that this overpressure is enough to blow off not only these windows, but also the beams or the steel that I have within the building could also get ruptured, which means that this building will go boom down. Okay, so it's not only the windows. How can I know? If I know the overpressure. Okay, so there is a way of how to calculate the overpressure, and then we're going to see the effect of that overpressure on the person or on the building. So all the ideas that we have around this overpressure and explosion, about explosion. So we have taken a lot of definitions here, and part of the definitions that we already have taken is the upper flow flammability limit and the lower flammability limit. Okay, so now as we have taken the definition, the next step that we are going to take, we want to understand the effect, or how do we now use those terminologies. I want to use the UFL, I want to use the LFL, I want to understand what happens to them if pressure or temperature increases. I want to understand the auto ignition temperature and what happens. And here is a very nice figure that we are going to stop at, and we are going to take that in another video. So here, in which you are going to see the upper flammability limit, the lower flammability limit, and the area where you have a flammable condition. However, this is if you have the fire, the fuel, the oxygen, and the source of ignition. Or if you exceed that auto ignition temperature, you will get into the auto ignition region. So it will get flame without even that source. However, if you go to a higher composition, you see here concentration, if you go to a higher composition, it will be not flammable. Or you go to a lower composition, which is the percentage volume percent, it will be also not flammable. all that is in the gas region. However, if it is in the mist region, it will not catch up fire. But however, if it just catches up of some of that mist becomes vapor, you will have the reaction or the combustion. What separates the mist or the liquid from that gas region? What separates it is the vapor pressure curve. In which we can calculate it through Antoine equation, depending on the temperature, right? Pressure depends on temperature. So that is the vapor pressure curve, in which it separates the mist from the gas where it have the flammable region. Which means that this saturation vapor pressure, it could move also to the left or it could move to the right? So it depends on what? On the saturation vapor pressure, which depends on the temperature. And what is the lowest point where we are going to have our first spark or flame? It is here, which is at the lower flammability limit. The first temperature in which we are going to have the first spark, which is the flash point. The fire point could be a little higher than that, which could be at this place here. So this is a very beautiful curve that sums up all what we have taken from definitions and flammability properties, and that gives us an idea about all the definitions together. Okay, great. So we are going to start tomorrow explaining this this part of the figure again, and from this figure we're going to go on and see how to use those different flammability properties to identify if a fire is going to catch up or not. Until then, I thank you very much and take care. Hopefully you have understood part of what we have taken today, and the continuity of that if this video is going to be in our next video. All the best, Dr. Bassam Al-Hamid. Ma as-salama.